Hey guys, Miss Pipel here. Today we're going to be talking about nuclear reactions. And so this is all related to reactions of the nucleus of an atom, right? So we're dealing with our protons and our neutrons. And we're seeing how those nuclei can break down, can join together, kind of what is all happening with the nucleus of the atom. So here we go. The first reaction we're going to look at is called a fission reaction. This is when we have a nucleus that splits into two smaller atoms, and it's usually started or instigated by having a neutron hit that large nucleus. When this happens, it releases a ton of energy, so that there's a ton of energy stored in that large nucleus that's then released when it's split into two smaller atoms. This is actually the type of reaction that is used in nuclear reactors. So we're going to talk about nuclear reactors more in class, just because I think that's something you guys should be familiar with. But that uses a fission reaction of a uranium atom, uranium-235. So that atom would split apart into two smaller nuclei. Up next is fusion. So fusion is when we have two smaller atoms fuse together to form one larger atom. So an example down here shows a hydrogen atom with a mass of 2 and a hydrogen atom with a mass of 3 coming together to form a helium atom. There's a leftover neutron and obviously a bunch of energy that's released. So this occurs on the surface of the sun. This is not something that occurs naturally on Earth at all. And it is something we're looking into harnessing for cleaner nuclear energy. But it is a little more dangerous and a little more harder to control. So fission is one atom breaking apart into two smaller atoms. Fusion is two atoms coming together to form one larger nucleus. Okay, so what we really think about, though, when we think about nuclear chemistry is what we call radioactive decay. So this is not necessarily the same. This is kind of a different category than fission or fusion. And what this is when you have an unstable nucleus. So it's uncomfortable with the number of protons and neutrons it has. And so in order to become more stable, it's going to release some sort of radiation or radioactive particle. So these are penetrating rays and particles, okay, emitted by that radioactive source that is mentioned above, okay? And what that means is that these particles can do damage. We specifically think about them doing damage to our cells or to even the nuclei in the DNA that's stored in the nuclei of some cells. So we're going to look at kind of which is the most dangerous in terms of that and which is the strongest in doing potential damage. There are three types of radiation we're going to look at: alpha, beta, and gamma. Those are the first three letters of the Greek alphabet. So that is why they're named that, and those are the Greek letters next to them, which you do need to be able to recognize. So again, these are the different types of particles that are emitted by an unstable nucleus. So it's going to emit these particles in order to try to get more comfortable energetically. We're going to start by taking a look at alpha decay. So alpha decay is when a nucleus splits apart and gives off an alpha particle. So an alpha particle is, the symbol is this 4,2He that you see up here. Okay, what I'm drawing on the right here is if that was kind of in picture format. So that would be two protons with two neutrons. And that's all it is. It's just a helium nucleus. And so that's why the symbol is 4,2He. Because it doesn't have any electrons with it, it does have a positive 2 charge, but we're not as concerned about that. We're mostly concerned that you recognize this symbol as an alpha particle. So an example would be a thorium nucleus here that has a mass of 230, and it decays by giving off a helium nucleus or an alpha particle. Okay, when it does that, the leftover, or what we call the daughter atom, is this radon 226. So the thing that we need to be looking at, though, that this is our alpha particle there. Alpha particles are pretty large, so they are blocked pretty easily, mainly by paper or clothing. Your skin is a good protector for your internal organs and things like that from alpha particles. So alpha particles are really not that dangerous to us, but we can kind of harness them. And one thing we're going to look at is something called targeted alpha therapy, which is a treatment for cancer. And so it's an alpha emitter that is directed at cancer cells. So the goal is for that alpha emitter or those alpha particles to get into the nucleus of the cancer cell and to do some good damage to that DNA so that you can stop the rapid growth, the rapid mitosis, or the rapid reproduction of those cancer cells. So that would be using alpha particles. So that's a practical use for something that would be an alpha emitter. All right, next up is beta decay. So beta particles are emitted during beta decay, and their symbol is a little bit different. So it's not actually an element symbol there, it's just an E here. It's got a mass of pretty much 0, or we just indicate that it's 0, and then it's the opposite of a proton, and so that's why its atomic number there is a -1. It's pretty much like an electron. Because that mass is way smaller than what we saw with our alpha particles, right? The alpha particles had a mass of 4, and these guys have a mass of 0. So these move way quicker, and so they need something a lot more dense in order to block them. So what we consider the minimum for blocking a beta particle would be thin pieces of metal, like aluminum foil, a thin piece of copper, metal foil of some kind. And kind of a fun fact, bananas, the potassium in bananas sometimes can be a radioactive isotope of potassium. So if you were to hold a Geiger counter up to a banana, it might actually click because it might be a little radioactive. So kind of interesting. Nothing that can harm you. Our bodies can take a certain amount of radiation, so nothing to worry about, but just kind of a fun fact there. Our last type of radiation is gamma radiation, and gamma radiation is kind of the highest energy and the most dangerous of all of the types of radiations that we've looked at. So it doesn't have any mass, there's no charge, it is actually just a wave, or what we call a photon, and we'll talk more about that later on this unit. And it generally comes with alpha or beta radiation. But the symbol for this one that you'll see is 0 mass, 0 atomic number, and a gamma symbol, which is just kind of a loopy Y there. This is so quick moving, it is has so much energy that it requires a lot for it to be blocked. And so we would actually need a thick wall of lead or concrete. And you can see in the picture up here that your alpha particles are blocked the easiest. Then you have beta particles that would be blocked by something like aluminum. And then you actually need a thick piece of lead to block your gamma waves. And as you can see all the way on the right here, not everything gets blocked. If you guys have ever heard of the nuclear meltdown in Chernobyl, there's a huge radioactive pile of kind of leftover material from that nuclear power plant and that meltdown. It's so radioactive that they have this thing built over it called the sarcophagus, and it is a mixture of lead and concrete, and it's like feet and feet, I think up to 10 feet thick, to try to contain some of that radiation to protect, the environment around that. So gamma radiation is super penetrating, is pretty dangerous, and needs a very dense, thick wall of lead or concrete or other dense material to be stopped. Okay, so you've seen a couple of these equations as we've gone through this presentation, and really what you guys need to be able to do with this information is, one, fill in the blanks of these types of reactions. You guys can see there's blanks here, and our job is to fill those in. And secondly, to identify what type of reaction we're dealing with. So our types of reaction are fission, fusion, and then we have alpha, beta, and gamma radiation, or reactions that we can try to solve here. So we're going to start with this first one, and I'm going to walk you through how to fill in the blank first. So in a chemical reaction like this, we kind of can treat the arrow like an equal sign. And so all of the protons and all of the neutrons that we're dealing with here have to be accounted for on both sides of my equal sign. And so what we're going to do is we're going to make sure that our top numbers add up to be the same on both sides of the arrow, and the bottom numbers add up to be the same on both sides of the arrow. So I'm going to start with the top number here. We're looking at this first example at the top. The mass there is 242, okay? On the right, I have 4 from that particle right there. And so my question is, okay, what plus 4 will get me a total of 242? So the number I can plug in there would be 238. Let's try that again because that's pretty messy. So 238 would be my mass there. Okay, same idea for the bottom numbers. The total on the left here is easy to find because there's only one thing on the left, so that's 94. So 2 plus something has to give me 94. So that would be 92. So that's pretty easy in terms of the math, hopefully. Everything on the top has to add up to be the same on both sides of your arrow, and everything on the bottom has to add up to be the same on both sides of your arrow. Okay, now I need to figure out what symbol goes here. Well, remember that in this notation, this bottom number here represents the atomic number. So I need to find element number 92 on the periodic table. And it turns out that is uranium, and so we would just put a U there. So I'm going to rewrite that a little bit clearer, hopefully, over here. So this is what that should look like in that blank. A little bit clearer. Okay? And then I want to identify that as either a fission, fusion, alpha, beta, or gamma reaction. And so what we're looking for are kind of some clues. So I have only one thing on the left, and it splits apart into 2 different things, this helium and this uranium. But we need to remember that helium is the same thing as an alpha particle. And so this is actually going to be alpha decay. Okay? So, looking at this second example here, I'm going to kind of clean up a couple things around here so that we can very clearly write and read what we have going on. So this is the same deal. This time though, we're going to fill in our blank on the left side of the reaction. So the top numbers here, 32 plus 0 on the right, gives me a top number here of 32. Then on the bottom, I have 16 plus -1. And so that means I'm dealing with 15. So we have to be careful with that negative sign there. It truly is a negative. So 16 plus -1 gives me 15. Okay, so now I need to look at my periodic table and find element number 15 in order to fill in the symbol there. And that is phosphorus, so P. Then after I fill in the blank, I need to figure out what type of reaction we are dealing with here. Well, right away I notice this symbol that's a little bit different than our normal isotope symbols, and I'm going to recognize that as a beta particle. So when I have a beta particle, I know I'm dealing with beta decay. All right, I'm going to do one more of these for you guys, this next one, because it's a little bit different. So this is still the exact same premise. We're still going to make sure all the top numbers add up to be the same on both sides, and all the bottom numbers add up to be the same on both sides, because we got to make sure all of our protons and neutrons are accounted for in this reaction. Nothing disappeared, nothing kind of was created out of nowhere. So I'm going to start with the bottom number this time, and you might see why in just a moment. But here on the left, I have 98. On the right, I have 3, and that's a symbol for a neutron. So that might be something to write down in your notes, that that is a neutron. But I have 3 of those, so I need to take that into consideration. But for our atomic number for neutrons, that's 0, so it doesn't really matter. And so the total on the left for the bottom numbers is 103. So 98 plus blank is 103. So hopefully we can do that in our heads and know that that's going to be a 5. Then we can look at the top numbers. Okay, I have 252 on the left here, and then I have 259 plus 3 neutrons. So that's going to be 259 plus 3, which is really going to be 262 for the total of my top numbers. So again, this 3 applies to that whole thing, and so that means 3 neutrons and a total mass of 3 coming from that piece, plus my mass of 259 from this guy right here. So for a total of 262. So I need 252 plus something to equal 262. Well, that's going to be 10. So 252 plus 10 is going to equal the 262 total I have on the right side. Then I'm going to look at my periodic table and find that number 5 is boron. All right, so that's how I can fill that one in. The last part of that is to identify what type of reaction we have going on here. Well, I have one atom plus a second atom on the left side, and that forms a new atom with some leftover neutrons. Okay, and so that is going to be what we call fusion. I have 2 atoms coming together to form one larger atom. So 2 nuclei coming together to form one larger atom, and then it's okay that I have some leftover neutrons there. That's totally fine. All right, so we are going to do some more examples of these in class, and this is your assignment sheet. Practice 2.3 is working through some of these, and we'll talk more about them in class tomorrow. I do want to give you a little bit more information, though, before I go, about how to identify these types of nuclear reactions. So this is kind of a generic guide for how you can match your reaction with one of the types we looked at. So fission reactions are going to have one atom, and their neutrons are always going to be on the left. Okay, these squares here are representing the arrows. Unfortunately, this app changes what those look like. So fission, you have your neutrons on the left to start that reaction, right? That's our trigger for our atoms to start to split. Then fusion, you have 2 atoms, and then you're going to have one bigger atom on the right plus some neutrons, like that last example that we looked at on the previous slide. And then finally, decay, you have 1 atom, and then it's going to produce a second atom, which is called the daughter, and either an alpha, beta, or gamma particle. Remember alpha, you're going to see that 4,2-He. That one's probably the hardest to identify because it looks like a normal atom, but you just need to associate that in your brain with an alpha particle. Then you have beta, which is going to be that 0, -1e, and then you have gamma, which is 0, 0, and your loopy gamma symbol there. So this can kind of serve as a guide for you to identify those types of reactions. I'll answer any questions and go over some more examples in class tomorrow. Hope you guys have enjoyed your weekend.